thanks for watching, and today we'll do a little bit of practice with the chain rule or the Chen Lu, but this time more challenging problems. So let's see if you're up for the challenge or not. So let me just remind you the chain rule. It just says the derivative of f composed with g, it's the derivative of f at g times the derivative of g. So again, you first differentiate the outside function while leaving the inside intact, and you multiply it by the derivative of the inside function. So, first challenge problem. Consider f of x equals x e to the minus x, and let's find the 1,000th derivative of f. Usually there are no stupid answers, but one stupid way of doing this is calculate f prime, f double prime, f triple prime, f quadruple prime 1,000 times or something until you get f of 1,000x. So that's definitely not what we want to do. Instead, actually, let's start the same way, but let's see if there's a pattern. So f of x is x e to the minus x. F prime of x, again, it's the derivative of x e to the minus x. And first you use the product rule, so differentiate that to get 1 times e to the minus x plus x times the derivative of this, for which we use the chain rule now. So e to the minus x, because the outside function is e, times the derivative of minus x, which becomes minus 1. And in fact, what we have is e to the minus x e to the minus x, which you can factor out as 1 minus x e to the minus x. Which doesn't really tell us much, but now let's calculate the second derivative. So in other words, the derivative of this, so 1 minus x e to the minus x prime. And so you first differentiate that to get minus, and you leave this intact, plus 1 minus x times the derivative of that, which becomes minus e to the minus x. And again, you can expand this out, minus e to the minus x, minus minus e to the minus x plus x e to the minus x, which, if you want, factor out e to the minus x, and you get minus 1 plus x, which becomes x minus 2 e to the minus x. Okay, so we get f prime is 1 minus x e to the minus x, f double prime is x minus 2 e to the minus x. We're still not sure what the pattern is, so let's continue. Let's calculate f triple prime of x. So the derivative of this, so x minus 2 e to the minus x prime. And again, you use the product rule, so derivative of this, which is 1 times e to the minus x, plus x minus 2 times the derivative of that, minus e to the minus x. So this, if you want, becomes e to the minus x plus 2, if you want, minus x e to the minus x plus 2 e to the minus x. And that, if you want, becomes 1 minus x plus 2, which becomes 3 minus x e to the minus x. Okay, so I think now it's a little bit clearer what we have. So let's see the pattern. We have f prime of x, which is 1 minus x e to the minus x. F double prime of x is x minus 2 e to the minus x. F triple prime of x, it's 3 minus x e to the minus x. And if you want, if you're still not sure of the pattern, you can calculate the fourth derivative of f. which I think becomes x minus 4 e to the minus x. So notice what we have. F prime of x, 1 prime is 1 minus x e to the minus x. F double prime is x minus 2, like 2 derivatives, then 3 derivatives minus x, and then x minus 4 derivatives. So what's interesting is, it seems that this alternates between something minus x and x minus something. What is that something? It's the number of derivatives. So it looks like we have the following. The nth derivative, and it has to do with even and odd numbers. For odd numbers, it's something minus x e to the x, where that something is n, n minus x e to the minus x, if n is odd. And if n is even, we have x minus the number of derivatives e to the minus x. N is even. So the question is, what is f to the 1,000? So the 1,000th derivative. Well, in that case, we're in the even case here. So we get x minus n e to the minus x. So in this case, x minus 1,000 e to the minus x. Very neat. And by the way, how can you write this in one formula? You'll see if you do sequences, if you want stuff to alternate, you do minus 1 to the n. So in general, what this becomes, it's minus 1 to the n, x minus n e to the minus x, if you're curious about this formula. All right, so I thought that was very interesting, and again, sort of showing that you have to try out a couple of cases until you see a pattern, because in fact that's how math is created. You don't really have a proof ready already in your head. You just try stuff out until you see a pattern and you can formulate a result. All right, now moving on to the next problem. So far we've learned how to do the derivative of f composed with g prime, but the question is, what is the second derivative? And the only trick to notice really is that it's the derivative of f composed with g prime and then prime. And now we can just use the chain rule, so that becomes f prime of g of x times g prime of x. And you want to prime that, so just use the product rule, and we get f prime of g of x prime times this, times g prime of x, plus f prime of g of x times the second derivative, which is g double prime of x. And for this, let's use the product rule, the chain rule again. And notice now the outside function is f prime, so you differentiate that again to get f prime prime of g of x times g prime of x. So that is this part, but remember you're multiplying it by g prime of x. And then plus f prime of g of x times g double prime of x. And what you end up with is f double prime of g of x times g prime of x squared plus f prime of g of x times g double prime of x. Of course, no one in their right mind would just use this formula directly. It's easier just to use the chain rule twice, I think. Okay, the next one is quite tricky, I have to say. It's the following one. Show that Because so far we used, when you use sine or cosine and you do the sine of theta or cosine theta, so far we use radians. But the question is, what if we use degrees? And actually, you should be very grateful that we're not using degrees, because it turns out the differentiation formula becomes much more complicated. And so, show that if theta is measured in degrees, then actually the derivative of sine isn't cosine, but pi over 180 cosine of theta. So you see, this is why we use radians, because in order to get rid of this factor, pi over 180, but this is another great instance of the chain rule, because we have two situations. On the one hand, sine in this case is in degrees, but we also know we can write sine in radians. And the chain rule really says how those two derivatives are related. So remember the equivalence between degrees and radians. 180 degrees is pi radians. So theta degrees becomes rad radians. So it's pretty rad, I would say. And so using proportionality, I think you get rad equals pi theta over 180. And so in particular, I believe theta becomes 180 over pi radians. You get, makes sense. If radians is pi, you should get 180 degrees. And then the rest is just using the chain rule formula. So d sine over d theta, that's just d sine over d rad times d rad over d theta. Okay, I don't even know why I did that. We don't need that actually. Now, what is the derivative of sine when the angle is in radians? Well, that's precisely the formula we've learned. So d sine over d rad becomes cosine. Cosine of what? Cosine of your angle. So cosine of theta, and d rad over d theta. Well, we just found that radians is pi over pi theta over 180. So the derivative of that with respect to theta is just pi over 180. So in the end, we get cosine theta times pi over 180. And that is the derivative, if you want, of sine of theta, where theta is in terms of degrees. So again, I think it's a good problem in understanding the relationship between the same variable but measured with respect to two different variables. So here sine is measured with radians and degrees, and we have a formula here. All right, next one. How about the derivative of absolute value of x? Well, I mean, it's not differentiable, but not differentiable at 0, but you can differentiate it in other, if x is non-zero. And the trick is just to notice that absolute value of x, it's square root of x squared. Or in other words, square root of x squared is absolute value of x. And now you can just use a chain rule. So 1 over 2 square root of x squared times 2x. This cancels out, and we get x over square root of x squared. And that's just x over absolute value of x. So in other words, the derivative of absolute value of x is x over absolute value of x. And in fact, it makes sense Because if x is positive, this just becomes x over x, which is 1. And if x is negative, this becomes x over minus x, which is minus 1. And that's precisely what absolute value is. It's x here, so the derivative should be 1. And it's minus x here, so the derivative is minus 1. But the neat thing is, this is more compact, which is shorter formula, and also some analog of this holds in higher dimensions. Next one, actually the next two are one of my favorite problems. So let's do the derivative of, let's see, sine to the n of x times cosine of nx. Okay. This, and then again just use product rule and chain rule. So the derivative of this, which becomes n sine to the n minus 1 of x. Because this is sine of x to the nth power, so the outside function is x to the n, so n x to the n minus 1, and times the derivative of the inside function, which is cosine of x. So that is the first part of the product rule, and you multiply that by g, so cosine of nx, plus f, which is sine to the nx, times the derivative of cosine nx, which becomes minus sine of nx, times the derivative of nx, which is n, and of course you could leave it like that, but it's not very nice. It's best to just simplify it a little bit, and in fact it's a quite nice simplification. So let's look at the common terms. So there's an n here, there's n sine to the n minus 1, and there's actually sine of n, sine to the nth power, which is the same as sine of n minus 1 to x times sine of x. So there's also actually a common factor of n sine to the n minus 1, which gives you n sine to the n minus 1 x times, now, cosine of x, cosine of nx, minus sine of x, sine of x, sine of nx. And you may notice this is of the form cosine of A, cosine of B, minus sine of A, sine of B, which should remind you of cosine squared minus sine squared, which is cosine of 2x, but here we get cosine of A plus B. And that is n sine to the n minus 1 of x of cosine of x plus nx. And so in the end, we get that it is n sine to the n minus 1 x times cosine of, if you want, n plus 1 x. How nice is that? In other words, we lose a power of n here from the left function, but we gain an extra factor of 1 on the right function. So it's kind of, you lose some, but you also get shifted some. So that's great. And last but not least, also a very interesting limit. The limit as x goes to pi of e to the sine of x minus 1 over x minus pi. Now, of course, if you know L'Hopital's rule, you can do it with L'Hopital's rule, but it's not fun. And also, strictly speaking, in this section, we don't know L'Hopital's rule yet. So let's see how to figure this out. Well, we have an x minus pi, so it should remind you a little bit of a derivative. And in fact, if you evaluate this at pi, so e of sine of pi, that's e of 0, so that is 1. So in fact, this is nothing else than this limit, e of sine of x minus e of sine of pi over x minus pi, that's nothing else than the derivative of this function at pi. So that is e of sine of x prime, but at pi. And by the chain rule, this becomes e of sine of x times cosine of x at pi. And that becomes e of sine of pi cosine of pi. And that is e of 0, which is, again, we just calculated it to be 1 times minus 1. And the answer is minus 1. So how neat is that? Again, without really, well, kind of we use L'Hopital's rule implicitly, but really without even knowing this rule, we're able to do that. Alright, I hope you like this little Chen-Lu challenge. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.